As a result of their violent thermonuclear reactions, stars produce massive amounts of light, which illuminates the night sky and, in the process, heats up any planets in their vicinity. Stars also produce the heavy elements that make up most of the matter in our universe. Astronomers and astrophysicists have made great strides in understanding how stars work, and they can now even predict. I'm Alex Mullen, and you're watching Astromullen. Join me today as we explore the fascinating world of exotic stars. Some of these stars can resemble black holes and dark energy, which is why they are so mysterious. We will also discuss the duration until our sun runs out of fuel and turns into a red giant. But that's not all. We will also think about stars that we've never seen before, stars that astrophysicists say could theoretically exist, including ones that are literally composed of vacuum, are going to be the focus of a plethora of recent scientific investigations, with some shocking developments in the field of quantum mechanics. In this video, we will delve into all of this, from the fundamental physical theories to the most outlandish theories, beginning with a basic understanding of how stars function. Our first stop will be the Sun, the most prominent star in the sky. Being composed of gas and plasma rather than solid matter, its surface is too hot for humans to stand on. Since the Sun's gravity would naturally draw you in toward its core, you might be wondering why the surface gas isn't being drawn in as well. Well, the answer is that the pressure emanating from the Sun's core acts as a counterbalance to the gravitational pull. This pressure is primarily caused by the radiation that the Sun's fusion reactions produce. This radiation is also responsible for the transfer of heat and light from the Sun to Earth, whether you view it as individual photons or as waves in the electromagnetic field. A balancing act between inward pulling gravity and outward pushing pressure is a feature of pretty much all known types of stars. What differentiates different types of stars is the source of this pressure. For our Sun, the pressure comes from fusing. Radiation pressure, on the other hand, wouldn't be enough to prevent you from falling into the Sun, but it's just enough to keep the Sun's relatively light gas from collapsing in on itself. When the Sun's hydrogen supply runs out, which should happen in around 5 billion years, it will transform into a red giant star and start producing pressure by fusing helium into heavier nuclei like carbon and oxygen. Eventually, when the Sun runs out of helium and all the other light elements that could be used as fuel for nuclear fusion, it will collapse into a small star called a white dwarf. Since fusion is no longer happening, white dwarfs are sometimes referred to as stellar remnants instead of. It turns out that when fusion stops, the gas in a white dwarf's interior becomes so dense that a new kind of pressure called electron degeneracy pressure arises. This effect is entirely quantum mechanical and is the same one that makes it impossible to put your hand through solid objects. Electrons can't get too close to each other without releasing an enormous amount of energy. However, some stellar remnants are so dense that this pressure becomes too great to bear. When a star uses up all of its nuclear fuel and its core is still heavier than the Chandrasekhar limit, the core will collapse in on itself until it becomes so dense that an even stronger form of quantum pressure called neutron degeneracy pressure emerges. This is because the core is so massive that not even electron degeneracy pressure can counteract the pull of gravity, which is referred to as the Chandrasekhar limit. A stable white dwarf cannot be heavier than 14 times the mass of the Sun. Neutron stars are the smallest and densest known class of stellar objects. You may be wondering how heavy a neutron star can be without collapsing under its own gravity. The maximum mass that a neutron star can have while still being supported by neutron degeneracy pressure is approximately 22 times the mass of the Sun. Any heavier than that, and the star would continue to collapse. From the outside looking in, these stars would become so dense that all we could see was a black hole. However, scientists began to wonder what would happen to a star that collapsed, given that neutron degeneracy pressure is the strongest force that ordinary matter can exert. This could be the fate of some of the most massive stars we've seen in the universe. Isn't composed of regular stuff? What new kinds of stars could exist if exotic forms of matter could theoretically generate pressures higher than the neutron degeneracy pressure? One could assume that stars could keep getting smaller and denser than neutron stars as long as they were propped up by even greater pressure, and that the only limit to how tiny they could get would be the point of no return, where they would. This is almost true, but not quite. In 1959, physicist Hans Adolf Ball demonstrated that no star composed of realistic matter with positive energy density and pressure could be smaller than 9/8 times its fart shield radius. This may not sound like a big difference, but it means that any realistic star would have to be noticeably larger than a black hole, making it much easier to distinguish between the two. Theoretical stars that could resemble black holes in appearance became a major headache for astrophysicists when physicists started to speculate about stars that Dow would consider less realistic. For instance, what if a star's composition permitted negative pressure in some areas and positive pressure in others? In this case, Ball's limit wouldn't apply, and the star would be smaller than 9/8 times its fat shield radius. Back to the main point. What exactly would these exotic stars with negative pressures look like? Tolman, Oppenheimer, and Volkoff came up with an answer that is even more bizarre than you might expect, since every time they found something they believed to be a black hole, they now have to qualify it as either a black hole or an extremely compact object mimicking one. Despite their deep conviction that it's a black hole, this has become standard practice. The Tove equation, which was first proposed in the 1930s and now simply known as the star stability equation, describes the change in pressure as one moves away from star center. If the star center had a very negative pressure, it would have an attractive pull instead of a push. According to the T equation, for a star to remain stable and in equilibrium with its own gravity, its pressure would have to do something really out of the ordinary, such as blow up to negative infinity at some point. When the pressure at the star's core is precisely equal to and opposite to its energy density, the star will reach its outer surface, where it will eventually drop to zero. The precise location of this infinite pressure, however, is dependent on the central pressure, so it is possible to fine-tune the central pressure to maintain a finite pressure all the way to the star's edge. In this particular instance, the top equations will govern this process. This star doesn't sound like any other star we've seen before, but it's beginning to sound like a mysterious component of our universe dark energy. The pressure and energy density are equal and opposite throughout the entire volume of the star, right up until its surface. If you've seen any of our other episodes, this might ring a bell or two. We've never seen anything like it. Gravitational vacuum stars, or gravars for short, are unusual exotic stars with characteristics unique to vacuum energy. The zero gravitational force inside these stars is the result of a balance between the positive and negative forces of gravity, which cancel each other out. Additionally, the pressure inside gravastars is constant, so there is no pressure gradient to cause any kind of push in either direction. Imagine being inside a gravistar, neither pulled in nor pushed out, floating freely like a real vacuum. Another interesting thing about these negative pressure stars is that as you approach their special limit, the point at which the infinite pressure surface is pushed out to the star's edge, their size approaches that of a black hole with the same mass. This brings up two important questions that have recently been asked. A great deal of interest among physicists has focused on two main questions. First, how can we identify black holes from other compact objects observed in galaxy mergers and at their centers? And second, if gravastars do exist and are distributed throughout the universe, could they be the dark energy responsible for the acceleration of the universe over the last 5 billion years? To address the first question, physicists look to the primary difference between black holes and other compact objects. An event horizon is a characteristic of black holes that prevents matter from falling into or even touching their surfaces. On the other hand, exotic stars that are slightly larger than their SH-shelled radius do not have event horizons and may be able to emit light and other forms of information. Objects without event horizons may also exhibit different gravitational wave signatures compared to those with them. We could differentiate between black holes during mergers by measuring and analyzing their gravitational waves using observatories like LIGO. However, it turns out that stars that are small and dense enough can still be hard to tell apart from black holes. Currently, Our best estimate is that the radius of the black hole candidates we observe in the universe is at least roughly equal to the Schwarzschild radius. In some cases, this is just an estimate, but in others, we have calculated. In early 2023, an analysis spearheaded by physicists at the University of Hawaii discovered that astronomical observations of massive black holes showed that their mass was increasing at the same rate as dark energy would be expected to grow over time due to the expansion of the universe. This led to the inevitable conclusion that black holes must be composed of dark energy and that they are really. The conclusion was subject to intense debate, with astronomers claiming that the observational data analysis was flawed and theoretical physicists arguing that black hole growth has nothing to do with the expansion of the universe. Despite the excitement surrounding the idea of dark energy potentially existing as GRA stars, it appears that the scientific community will not be accepting this explanation. Leave your thoughts and questions in the comment section. If you're an Astrom fan, you're probably already aware that Betelgeuse isn't your average star. It's a red supergiant in the Orion constellation. But how do you feel about the topic? If it behaves like a black hole and talks like one, should we just call it a black hole? Or should we consider the possibility that black holes could really be secret stores of dark energy? Constellation, which is located approximately 650 light-years from Earth, is the second largest star in the sky and the 10th brightest star overall, not including the Sun. A few years ago, Betelgeuse made news when the once bright supergiant star seemed to be dimming, suggesting it might be about to burst into a supernova. However, that wasn't the only surprise Betelgeuse had in store for astronomers. Measurements from the Elmer array of telescopes have revealed that Betelgeuse is actually rotating at a mind-boggling rate of every 20 years, which may not sound very impressive, but for a star the size of Betelgeuse, it means that its surface is spinning at a speed of 18,000 kilometers per hour, or about 5 kilometers per second. This is 10 times faster than our own velocity on Earth's surface, and for a massive supergiant star, it practically breaks the laws of physics. My name is Alex Mullen, and you're watching Astromullen. Join me today as we explore the peculiar surface of Betelgeuse and uncover the mysteries behind its unbelievable rotational speed. Let's begin with the basics. The angular diameter of the Moon is approximately half a degree, and its features can still be made out with the naked eye. Jupiter's angular diameter is 1/100th of a degree, but its features are still discernible through a telescope. Now, what about Betel? There are a couple of ways to measure the rotation of objects in the night sky. If the object is large enough, like the Sun, Moon, or one of the planets in our solar system, it's easy enough to point a telescope at it and observe its features move in real time. The supergiant star JUICE is located just 650 light-years away from Earth. Despite its size, Betelgeuse's angular diameter is 1,000 times smaller than Jupiter's, making it appear completely blurry to even the most powerful telescopes. Fortunately, there's an alternative method that relies on a simple effect called Doppler shift. You may be familiar with this method. It is also cause the siren's pitch to change as an ambulance goes by. When the ambulance is coming towards you, the sirens sound higher pitched because the sound waves reach your ears at a higher frequency than when the ambulance is stationary. However, as soon as the ambulance starts to move away, the effect is reversed and the sound waves reach your ears at a lower frequency, resulting in a lower pitched siren. What you might not realize is that the Doppler shift also affects the light waves that bounce off the ambulance, similar to how it influences because light travels at 1,000,000 times the speed of sound, we would need an extremely fast ambulance to detect the optical Doppler shift. We may not have any ambulances on Earth traveling at 5 kilometers per second, but when they do, the visual effect changes from slightly blue to slightly red. The sound waves from the siren cause the higher frequency light to appear bluer as the ambulance draws near, and the effect reverses as it moves away. All kinds of speeds are fair game in space, which brings us full circle to Betelgeuse. When a star rotates, half of its surface moves towards us and half away. This causes the star to emit a gradient of colors, which can be seen through telescopes. If the star is too blurry to discern its features, we can still infer its direction of rotation by measuring the difference in the blue and reddish hues. The redder ones have higher frequencies, which allows us to calculate the rotational velocity of the star. Astronomers used this method to analyze the data collected by ALMA and came to the conclusion that Betelgeuse's surface was spinning at 5 kilometers per second. Now, this is all well and good, except that according to the known laws of spinning stars, a red supergiant like Betelgeuse shouldn't have a rotational speed of 5 kilometers per second. As an example, the rotational speed of AN is roughly 2 kilometers per second, but it's also 1,000th of that speed. The Sun is much smaller and lighter than Betelgeuse, but if it were to engulf the entire inner solar system and approach Jupiter's orbit, its velocity would plummet to just 2 meters per second to conserve angular momentum, just like an ice skater slows down when she spreads her arms. Similarly, if the Sun were to grow 10 times heavier to match the mass of Betelgeuse, its velocity would plummet to 2 meters per second. Betelgeuse's spin seems to be defying all expectations. So what's going on? One possible explanation is that it gained its angular momentum through stellar cannibalism, which is basically when one star consumes another star, typically its companion, in a binary orbit. In scientific terms, this happens when the star's gravity gradually pulls away its companion's gas until only the innermost core remains. That gas carries most of the angular momentum of the companion star, causing the first star to grow larger and spin faster than nature would normally allow. But is this really the story of Betelgeuse's spin, or is something even more mysterious happening underneath? A group of researchers from Europe and China recently proposed that Betelgeuse's seemingly absurd rotation speed might be nothing more than a giant optical illusion. How could this be? Thinking back to what the team ALMA actually measured with their cutting-edge telescope array, we can see that Betelgeuse emitted slightly redder and slightly bluer frequencies of light than normal. This 50-50 split makes perfect sense because the star is rotating, so one half is moving towards us and the other half is moving away from us. You can see this in the green arrow in the image of Betelgeuse. Simulations of Betelgeuse have shown that its surface is a chaotic, turbulent place that is constantly bubbling under its own heat, like water bubbling in an oven. Each of these enormous bubbles propagates outwards at deadly velocities. One bubble can be 100 million kilometers across, covering a large fraction of the surface of Betelgeuse. What if, instead of being the only explanation for the color gradient detected by ALMA, one of these? Betelgeuse's surface becomes a mosaic of regions that are either moving towards us or away from us as observers on Earth. As a result of the Doppler shift, the light emitted from these regions is either blue shifted or red shifted. Even the most powerful spacecraft in the world wouldn't be able to stop these bubbles from hurtling towards you at speeds of up to 30 kilometers per second. Your only hope would be for the bubbles to burst and crash violently back onto the surface before they reach you. According to a paper that Rose wrote, there may not be any rotational effect at all. Instead, the ALMA observations could be picking up on a spectrum of light frequencies emitted by Betelgeuse as a result of surface turbulence. Astronomers may have been mistakenly attributing these shifts in frequency to rotation, as any physics student worth their salt can tell you. Astronomers at ALMA could not have mistaken one for the other if they saw a smooth gradient of colors emanating from Betel, since a rotating star should emit a uniform spectrum of light with a bluer than expected edge and a redder than expected one. In contrast, a turbulent star should create an asymmetrical patchwork of colors, with bluer patches representing rising bubbles and redder patches representing falling ones. It seems like the patchwork explanation is already out in the cold. In a perfect world, where gradients would represent rotation and patches would represent bubbles, Betelgeuse would be so far away that ALMA's image would be more blurry than an HD photograph. To compensate for the limited resolution of their observations, they simulate its surface and predict that the bubbly patches of red shift and blue shift will be mistaken for A. Approximately 90% of the time, the rotational gradient is negative. This implies that the astronomers at ALMA may have been deceived by the boiling surface of Betelgeuse into thinking it spins much faster than it actually does. As a result, astronomers are now pursuing a higher resolution study of Betelgeuse in order to distinguish between the two scenarios. Fortunately, there are better images of Betelgeuse that have been taken by the same telescope, but with longer exposure times. Unfortunately, for the impatient among us, the results of these analyses will probably take a few years. In the meantime, I'm interested to hear your predictions. Is Betelgeuse really spinning at 5 kilometers per second after devouring its companion star? Or will the new theory that this is all an optical illusion be proven? Please share your thoughts in the comment section. Have you ever wished you could witness? On a partly cloudy spring night in the west of Ireland, amateur astronomer John Birmingham was making his way home in the dark just before midnight. He would occasionally slow down so that he could look up at the stars with a sharp eye, scanning the night sky for familiar constellations, just like he had done before. Little did he know, in 2024, you would have the opportunity to witness what is arguably the next best thing: the explosion of the blazed star. Surprisingly, it just keeps exploding. He had seen the Northern Crown countless times, but this time he was stunned to see a new bright star in the familiar constellation. It was a recurring nova in the binary star T Cron Borealis, also known as the blazed star, an explosive astronomical event that happens only once every few decades. In 2024, those of us alive will have the unique chance to witness the same. Join me as we get ready to witness this remarkable stellar event. The star is actually a binary system of two stars locked in orbit with each other, which is a bit misleading given its name. The relationship between the stars determines when and how this recurring explosion, which captivated Birmingham's fascination more than 150 years ago on that cool spring night in Ireland, will occur again. The blazed star system's binary configuration is responsible for the nova explosion that happens every 80 years or so. It's believed that half of the stars in the sky are actually part of multiple star systems rather than solitary ones. Both stars in the system began their lives as average-sized stars like our Sun, but they're now at drastically different stages of their life cycles. In 5 billion years, the star will consume all of its hydrogen fuel and start fusing heavier elements. It will eventually become a red giant, potentially consuming Mercury, Venus, and even Earth. Between 5 and 10 billion years from now, the red giant will shed its outer shell, creating a gas nebula around a white dwarf. White dwarfs are the extremely dense and small core remnants of the once giant star. When they run out of fuel, they're often referred to as dead stars. During the next 10 trillion years, the two stars in the blazed star system will cool down until they stop emitting light and heat. They are both about the size of our Sun, but they are further along in their stellar evolution than us. This is why we will be able to see a recurring nova in 2024. It's all about the relationship between the two stars. As the red giant expands its outer shell, the white dwarf is constantly losing hydrogen to its neighboring star due to its enormous gravitational pull. As time goes on, it collects this material on its surface, acting like a cosmic vacuum cleaner. However, as the pressure and heat build up, the white dwarf eventually experiences a thermonuclear explosion, which releases all of the stored material. To better understand this process, think of the white dwarf as a party popper. You pull the string tighter and tighter, adding tension until it snaps. The blazing star's white dwarf is subject to increasing pressure and heat until it explodes, causing a nova explosion that can make the star appear 1,150 times brighter than usual. This happens around once every 80 years, as observed from Earth, which is 3,000 light-years away. So, how is this different from the more famous supernovas? Well, although the blazing star does undergo a massive explosion with each nova, called a classic nova, it does not destroy the white dwarf. Rather than destroying itself, a solid star will occasionally blast away material it has collected from nearby stars. When the pressure and heat get too much, it will be close enough to Earth for us to notice a noticeable change in its brightness. On the other hand, in order for a star to explode in a grandiose supernova, which could be millions of times brighter than a blaze nova, it needs to begin with more than 8 times the mass of our Sun. Although it is 640 light-years away, the red supergiant Betelgeuse, a star that frequently ranks among the top 10 brightest stars in our night sky, is the nearest star on track to undergo a supernova explosion in the not-too-distant future. However, from a cosmic standpoint, this star isn't expected to go supernova for tens of thousands of years. From a human perspective, it may be a little while yet. Though extremely unusual, Betelgeuse won't be the first time humans have witnessed a supernova. The Blah star isn't the only nova in recent history that has been visible to the naked eye, and the oldest record of a supernova, now called SN 1185, comes from Chinese sources. Picture this. Betelgeuse explodes in a supernova, and the star becomes as bright as a full moon and remains visible during the day. What a breathtaking sight! 185 AD astronomers recorded what was then known as a GU star that remained visible for an unprecedented 8 months. Since then, modern astronomers have been able to detect the explosion's remnants, confirming that the star had in fact burst into a supernova. Throughout recorded history, only a small number of supernovae have been visible to the human eye. Johannes Kepler, a German astronomer, recorded the most recent of these in 16004, when a supernova was so bright that it could be seen. The Blaze star, on the other hand, is predicted to be one of the most luminous classic novae of this century during the daytime in 2024. Classic novae, which are visible to the naked eye, occur more frequently than supernovae, but even when they do, they are rarely bright enough for the unaided eye to detect them. While supernovae are extremely rare and noteworthy, classic novae are more common. Astronomy, a star's apparent magnitude, is a measure of its brightness as seen from Earth. A star with a magnitude of 0 is brighter than a star with a magnitude of 1, which is brighter than a star with a magnitude of 2, and so on. Usually, a planet or star needs an apparent magnitude of about 65 to be visible to the naked eye on the darkest night for visual observation. From a different angle, the 7 stars in OA Major, often called the Big Dipper, have apparent magnitudes that vary from 48 for the faintest to 17 for the brightest. The night sky's brightest star, Sirius, has a magnitude of -144, and the daytime Z has a magnitude of -265. Yes, the apparent magnitude scale goes into the negatives. The Blaze star, which is normally 10 on Earth and invisible to the naked eye, peaks at a magnitude between 3 and 4 during the nova explosion that occurs once every 80 years. 2. It came out of nowhere to become one of the brightest stars in the sky. The term NOA comes from a Latin word meaning new. I can only imagine how shocking it must have been for people living before telescopes to see a new star appear. More recently, astronomers were surprised by Novus Centaur 2013, which was one of the brightest stars in over a century with a peak magnitude of 33. The last time the Blaze star exploded was in 1946, when it reached a magnitude of 3. This year, the star will appear even brighter than before. There is no set date for when the Blah star will explode, but scientists believe it could happen anytime in the second half of 2024. In the meantime, keep an eye on the star because it could become even brighter than Polaris, the North Star, which has a magnitude of 197. However, once it does explode, the show won't last long. The Blaze star may only be visible to the naked eye for a few days or a week before fading back into the darkness. The Blaze star can be found in a small semicircle-shaped constellation called the Northern Crown, which lies between Hercules and the kite-shaped Boats. If you trace the Northern Crown from the Boats constellation to the side closest to Hercules and end on the side closest to the explosion, the Blaze star should appear just below the last star. Keep an eye on the news in the sky to find out when the NOA explosion begins. Northern Hemisphere. And if you're lucky enough to have a powerful amateur telescope or visit an observatory, you might even be able to see this binary star before the nova starts. This would be an incredible opportunity to compare and contrast the two, and it would also serve as a reminder that even stars, which appear eternal and unchanging, can have incredible life cycles that include changes and explosions like cosmic fireworks. Each nova is rare and awesome, and astronomers can learn something new from them. You may have heard that modern science believes the universe to be 138 billion years old. It seems rather unfathomable how anyone could come to that conclusion, but actually, the how is not too difficult to understand. So, keep an eye on the night sky and maybe feel just a little bit luckier to be alive and to experience this here on Earth. This nova will undoubtedly be one of the most exciting astronomical events we will get to see in our lifetime. Most people either dismiss the question out of hand or take it at face value. In this video, we'll delve into the topic, but we'll also throw a wrench into the works by discussing the recently found age of a local star called the Methuselah star. This star is apparently older than the universe itself, which means it's 138 billion years old. How do we arrive at this figure? As it stands, we observe the universe expanding and cooling, with everything moving away from everything except for forces like gravity that hold things together and the speed of light. The expansion of the universe, measured by the Hubble constant, is currently occurring at a rate of 880,000 kilometers per hour per million light years. As a result, matter is becoming diluted and there is more space between things. Another less obvious consequence of the expansion of the universe is the red shift, which is the stretching of light wavelengths. These waves, which were initially emitted shortly after the Big Bang and had extremely high energy and frequency, are now reaching us as less intense, further apart. Energetic microwaves, also known as the cosmic microwave background radiation, are the reason behind the James Webb Space Telescope's infrared capabilities. This is because photons of light emitted by galaxies billions of light years away have shifted their frequency to the red, making them inobservable without an infrared telescope. A photon contains energy, and since a lower frequency wavelength indicates less heat, we can infer that the universe was once dense. It was once hot and compact, but now it's larger and cooler. How does this information help us calculate the age of the universe? Well, we must first assume a few things about it. Firstly, that it is uniformly dense on the largest scales. This seems incorrect because clearly the universe is not uniform. There are superclusters with extremely dense galaxies and supervoids with almost no matter whatsoever. However, when we zoom out far enough, everything appears to be the same, leading us to assume that the universe is homogeneous. Assuming the following three things. First, that matter is uniformly distributed throughout the universe. Second, that the laws and properties of the universe are the same in all directions. And third, that the Big Bang happened simultaneously in all locations. For those who are unfamiliar with this, you can watch my video on the subject here. If all three of these things hold true, then, according to the laws of general relativity, we can determine the age of the universe and its rate of expansion by using these assumptions to calculate distance and brightness. Interactions between celestial bodies, such as stars, supernovae, and galaxies, can provide light on a variety of questions. For example, why do dwarf supernovae always seem to be about the same brightness? If a supernova is fainter than expected, it could be farther away, so measuring its faintness can tell us how far away it is. By comparing it to clusters of galaxies, we can also detect fluctuations in the cosmic microwave background radiation, which provides a snapshot of the universe just a few 100 million years after the Big Bang. We now know that the universe is 68% dark energy, 27% dark matter, and 5% observable matter. However, we still don't fully understand what dark matter and dark energy are or how they work, but we can observe their effects. For example, dark energy is thought to be the driving force behind the expansion of the universe, since expansion would have slowed down by now if it weren't. We don't know what dark matter is, but we can observe its influence and even map out its mass distribution, like in this image. However, we can't observe it directly, and it's not necessary to know what it is for the purposes of this video. What matters is that it acts as a gravitational force, since otherwise galaxies and galaxy clusters would appear to have much more mass than they actually do. Universe's age, we know the present rate of expansion, or the Hubble constant, and how the red shifts light. We also know the universe's composition and its properties, and we can observe the evolution of galaxies and search for fluctuations in the cosmic microwave background radiation. By combining these three data sets, we can extrapolate back to the early stages of the Big Bang and have returned to the same 138 billion years with an estimated 99% accuracy. But another method has thrown a wrench into the works: measuring the age of stars. Some stars are extremely short-lived, going supernova in a few million years, while others could last for trillions of years. Of course, we haven't seen one that old for obvious reasons, and following star evolution, we haven't seen any older than roughly 132 billion years old. However, this does mean that large. Star Methuselah is a metal-poorer star, which means it is extremely old, extremely rare, and most importantly, it is relatively close to Earth, just about 200 light-years away. This allows us to study it relatively closely based on its evolution. It is estimated to be 145 billion years old, give or take about 800 million years, which means it may have debunked the 138 billion. I don't think we will see this figure vary more than about 1 billion years in either direction. Research in this field is still in its early stages, although it has been a topic of study for a while to determine the exact age of the universe. With the W1 and James Webb Space Telescopes set to launch soon with specific mission objectives to peer deep into the past, exciting times indeed. Oh, I must admit, I'm absolutely amazed by how far we've come. Who would have thought we could get this far a few hundred years ago? Of course, now we have more questions than answers, but that's just science for you. The Hubble Space Telescope, for example, has been imaging some truly breathtaking aspects of our galaxy and beyond for the past 28 years. It's a technological marvel that has greatly enhanced our understanding of the cosmos. No end, and that includes learning about the many different kinds of stars in our galaxy and how they've evolved over the years. In this episode, we'll take a peek at a few of the most unusual and interesting stars it has seen. And trust me when I say that some of them are absolutely stunning. Take, for example, Stellar Site 35 HH34, located close to the Orion Nebula. It's a Herbig-Hart object, or emission jet, from a very young star, and you can see the star still inside. Here we can observe stars in the process of formation relatively close to the Orion Nebula, a molecular cloud that is one of the closest star-forming regions to Earth. As the star releases a jet of gas from one of its poles, it speeds through space at hundreds to thousands of kilowatts per second. Eventually, this jet hits cooler material, heating it up, as seen in the bottom left. By astronomical standards, this event is very brief, lasting only a few thousand. This is Xe Tauri, a star system with two stars approximately the distance between our Sun and Pluto. For reasons that scientists do not yet understand, these stars have ejected a massive bubble of hot gas, which can be seen here. The stars in this system are HL Tauri and V11213 Tauri, and there are 36 more stars in the process of formation. This image has to be one of the most mind-blowing ones that Hubble has ever captured. HL Tauri is another young Tauri star that has been observed to expand rapidly over the past 5 years. Its protoplanetary disk obscures our view of the star, but its reflected light is coming from other sources, and it is also ejecting another Herbig-Hart object, number 150, in this direction. Lastly, we have E11213 Taur, a variable star with a spectacular disk surrounding it at a side-on angle to us. The star is once again encircled and fed by a molecular cloud, but what's clearly visible is a jet of gas, resembling a lightsaber, being blasted away from the star in both directions. This object shares many similarities with the other Higgs boson objects in this episode, but the image presents a different perspective. This protostar, which is located near the Orion Nebula, number 38 LL Pegasi, is truly remarkable. Now let's shift our focus to stars that are approaching the end of their lives. Rather than this brilliant star, we should look at the dark and mysterious spiral that lies next to it. It's one of the most exquisite geometrical objects in space. But what exactly is it? It's a preplanetary nebula, which means that a massive star is releasing some of its mass before it potentially explodes into a planetary nebula. The picture shows a material form in a spiral that is moving at 50,000 kilometers per hour. When combined with the distance between the layers, it is estimated to produce a ring roughly every 800 years. This is believed to be directly related to the fact that this is a planetary nebula, as planetary nebulas consist of extremely hot ionized atoms that emit their own light. On the other hand, preplanetary nebulas are reflection nebulas that are illuminated by the light that is reflected off of them. Another preplanetary NENE, HD 44179, is a unique nebula with a rectangular or an X shape. It is extremely difficult to observe from a ground telescope due to the Earth's atmosphere, which is why Hubble in space is so helpful. The orbital period of this binary star system is believed to be 800 years, which means that the spiral is caused by the motion of the stars as one of them loses mass. Scientists who don't know. Let's take a look at a different kind of star using RS Puppet. The bright star in the middle of the image is our focus, and something very strange is happening in this image. The exact mechanics of how this structure formed are unknown, but there is evidence that it is the result of another nearby binary star system, in which a star with a mass similar to our Sun shrinks in size before becoming a white dwarf. The remaining white dwarf will then emit ultraviolet light, ionizing the gas that is expelled into planetary nebula number 40. This star is a Cepheid variable, which means its brightness changes by a factor of 5 around once every 40 days or so. The star is encased in a beautiful dust structure, which allows us to observe its variable nature through light. Since echo light travels at extremely high speeds, but takes a very long time to travel across astronomical distances, we can see the light's precession away from the star, with some rings appearing darker as the star was dimmer and some rings appearing brighter as. Over the course of 5 days, Hubble captured images of RS Puus, a variable star that is both eerily beautiful and spectacularly brief due to the rapid mass loss through solar winds, up to 7 million km/s. Much of the material surrounding this star is actually the star's ejected mass, which is being further sculpted. Due to the influence of the solar winds, this star will eventually transform into a Wolf Ring star, which is a star type that is millions of times brighter than our Sun. However, at the moment, its intense heat makes it invisible to the human eye, and most of its radiation comes from the ultraviolet. Up until now, all the stars we have studied have been located within our own galaxy. While individual stars are usually difficult to see, in rare cases, massive galactic events can be observed across vast distances. This is the case with NGC 4993, a galaxy located 140 million light-years away, where an event even more spectacular than a supernova took place, a killer neutron star merger. In August 2017, the LIGO detected gravitational waves from the merger, and within 12 hours, the source of these waves was identified. Considering how bright and obvious it is from such a distance, I can't even begin to fathom what it would have been like if these neutron stars had collided within the same galaxy. This image is a tiny slice of the enormous Tarantula Nebula, which is located in the Large Magellanic Cloud, a satellite galaxy to our own. The resulting kilonova explosion will have released electromagnetic radiation at every frequency imaginable, from radio waves to gamma rays. Interestingly, it is thought that neutron stars colliding could be the universe's primary source of heavier elements like gold. If this is so, your jewelry will have a bit more of an edge. Although it may not be as visually appealing as some of the other nebula we've seen so far, I must admit that it does have its own appealing qualities. However, if its appearance isn't what makes this nebula stand out, then what is it? We'll get to that later. First, let's put in context. This is the Large Magellanic Cloud, the largest satellite galaxy of the Milky Way. It contains numerous nebula, including the one we're looking at today, the Tarantula Nebula. The Tarantula Nebula is the largest and brightest nebula in our galaxy. It's so bright that it would cast shadows at night if it were as near as the Ur Nebula in our Milky Way. Here we can see why it's currently undergoing extreme star formation. It's the most active star-forming region in the whole local cluster of. NGC 2070 is a star cluster located in the center of the galaxy. Its central concentration, or 136, is responsible for the majority of the light that illuminates the nebula. The cluster is quite large, containing an estimated 450,000 solar masses of stars. If you've ever wanted to know about the most massive and brightest star in the universe, your search is over. Our 136A1, a Wolf-Iris star, is among them. This star is 315 times heavier than the Sun and 87 million times brighter than the Sun. It is also one of the hottest stars in the universe, with a temperature of 53,000 degrees Celsius. Although it is the most massive star in the cluster, it is not the largest. Like all massive stars, it will likely collapse into a black hole at the end of its life. In the meanwhile, it has lost mass through the solar wind at a rapid rate, and scientists believe it has lost 50 solar masses since its birth. NGC 2070 is a merging cluster of two nearby clusters, one of which is believed to be only around 2 million years old. At first glance, it may not appear like there are enough stars in this image to constitute 450,000 solar masses, but the blue stars you see here are actually the cluster's most brilliant O-type stars. Interestingly, if we take a closer look, we can see that this cluster contains a star called 30-016, which isn't seen anywhere else in the area. The young star in question is only 1 to 2. 30-016, which is believed to be 9,000 solar masses, has been around for at least 1 million years and has traveled approximately 375 light-years from its probable home in the star cluster R136. It continues to travel at a speed of around 400,000 kilometers per hour. How did it end up out here? One theory suggests that it was once a star in a binary system that was kicked out by a much larger star. The other stars would have had to have been incredibly massive. Now 30-016 is an explorer, set to explore the vast expanse of the universe. In the Tarantula Nebula, there's an ancient star cluster known as Hodge 301. It's about 20 million years old and contains stars that are 10 times older than those in our 136. Out of the 40 stars in this cluster, at least 40 have gone supernova, whereas none have in our 136. This is because, due to the cluster's age, even the shortest-lived stars in Hodge 301 have completed their entire life cycles. Additionally, other stars in this cluster are on the brink of exploding in a supernova explosion. Keep an eye on this space because the first image we looked at was far from the Tarantula Nebula center. However, it is still part of the nebula and can be found in an area called NGC 2060, which is a star cluster too. Unlike our 136 and Hodge 301, the stars in this cluster are not gravitationally bound to each other. In fact, the stellar group will disperse entirely in a few million years. The cluster is currently around 10 million years old, and it contains some fascinating objects. In this region, the first thing to note is that NGC 2060Z is a supernova remnant that spans approximately 165 light-years. The supernova is believed to have happened between 4,000 and 5,000 years ago. According to this theory, there is a pulsar neutron star in this region around the same time as the supernova. However, it is not visible to the naked eye because it emits X-rays, which can only be detected by the X-ray telescope Chandra. The supernova bubble itself is located in the center of this object. Remainder of the pulsar spins at a dizzying rate of 2 million km/s, which is 100 times faster than the speed of light. The star is so distorted by centrifugal forces that an equatorial disk extends out from its surface, and it is believed that this runaway star was once a component of the same. This system is similar to the pulsar and had a role in its supernova explosion. Prior to the explosion, two blue stars would have been in an orbital relationship. One of them would have grown into a red supergiant, and, as it expanded, would have begun transferring its mass to the other star, causing it to spin faster. When the red supergiant exploded, it ejected the other star into space at an incredible speed, and VFTTS-102 fits this model perfectly because of its rapid rotation and its hurling through. As we continue to expand our view, we approach the outskirts of the Tarantula Nebula, which at its largest is an enormous 1,000 light-years across. As I've already indicated, this nebula is the most massive and active star-forming area in our local group of galaxies. If it were as near as the Orion Nebula, it would dwarf the Big Dipper by 2 orders of magnitude, and its brightness would make it appear as bright as SN 1987A, a supernova remnant visible during the day at the nebula's periphery, is the most impressive observational feature. At less than 30 years old, it is the youngest supernova we have studied thus far. The light it produced reached Earth in 1987, making it visible to the human eye. This explosion was the first to be detected since the 1600s, and modern telescopes have allowed us to examine it in great detail. It was a blue supernova, which means it was only about 1/10 as bright as a red supernova. I haven't had the opportunity to observe it, but I bet you're wondering what the ring-like structure is. It's actually the mass ejected by the star through stellar winds as it sputtered and coughed thousands of years before the explosion. The ring-like structure was initially illuminated by the initial flash of the explosion, but it was later illuminated by the supernova shock wave, which interacted with the rings and the star's interior. Based on real data, this artist's illustration of SN 1987 shows the cold inner regions of the exploded star's remnant. The patch in red represents an area where the ELMA telescope detected and imaged tremendous amounts of dust. It is in this dust that the leftover pulsar could be hiding. The debris from the shock wave is now a true supernova remnant, similar to Copia, which is illuminated not by the star's explosion, but by continual processes with the material beyond it. Since there has been no detection of the pulsar's location, another possibility is that it never transformed into a pulsar, but is now a black hole. Thank you for watching, and I'd like to extend my deepest gratitude to our astronauts on Patreon. Our community is growing, and I've enjoyed reading your comments and messages. If you're interested in becoming an astronaut and giving our channel more stability than the algorithm, you can find a link in the description. Once you're in, if you want to see the entire movie without ads, get your name added to the credits, and ask our team questions, you can do so by clicking the link to this playlist. Until next time,